Today we will discuss about the magnetic property in solid. Magnetism in solid mainly arises due to the spin motion and orbital motion of the electron. Major contribution of the magnetism mainly arises due to the spin motion of the electron, and the property or nature of the magnetism is arise due to the unpaired number of unpaired electron of the atom. Suppose an electron revolve around in a tiny circular orbit about a nucleus. Suppose a nucleus of charge E revolve around in a tiny circular orbit of cross section of area A. Due to the revolution or revolving, a current is generated in the loop. This amount of current can be expressed as I is equal to charge into frequency, and this current can be considered as a magnetic dipole moment, and this is equal to mu current into loop area. Suppose a solid contain a large number of atom, suppose n number of atom, and each atom or molecule consists a dipole moment mu. Due to the application of external electric field, this dipole moment is aligned along the direction of external magnetic field. As a result, the substance is said to be magnetized. We consider an elementary volume dV. Due to this elementary volume, the total number of magnetic dipole moment in the substance is equal to summation of mu I, where mu I is the dipole moment of the ith atom. The total magnetic dipole moment is equal to I is equal to 1 to n, where n is the total number of atom or molecule. So, we define the magnetization M, that is equal to limit delta V tends to 0 delta mu by dV, delta mu by delta V. This is called magnetization, and experimentally it is found that if the magnetic field intensity is not too high, then the magnetic dipole magnetization M is directly proportional to magnetic field intensity, or magnetization M is equal to some constant into H. This proportionality constant chi is known as susceptibility of the material. Susceptibility of the material. So, susceptibility chi can be expressed as magnetization per unit magnetic field. Depending on the susceptibility, the material can be expressed or can be classified into 5 categories. On diamagnetism, to paramagnetism, three ferromagnetism, four antiferromagnetism, 5 fifth, ferrimagnetism. Today we will discuss about only paramagnetism. The paramagnetism of a substance mainly arises those atom or molecule which have permanent magnetic dipole moment, and this can be explained, or its susceptibility can be explained on the basis of classical theory and quantum theory. First we discuss the classical Langevin theory. Classical Langevin theory. Langevin considered that a paramagnetic gas consists of n number of atoms, and this atom or molecule are freely rotate, that is the interaction between two atom or molecule or dipole is negligible. When the external magnetic field is applied on the substance, the magnetic dipole moment suppose in absence of magnetic field, when magnetic field is 0, the magnetic dipole moment are randomly oriented. So the net magnetization of the substance is equal to 0. Magnetization of the substance is equal to 0. When external magnetic field is applied on the substance, on magnetic material, H is not equal to 0, the magnetic dipole moment are aligned along the direction of magnetic field. As a result, we get a magnetization. Suppose mu is the magnetic moment of each atom. Mu is the magnetic moment of each atom. And the magnetic field, suppose H is the magnetic field intensity applied on the substance, and due to application of this field, the magnetic dipole moment align along the direction of magnetic field. But due to thermal agitation, this magnetic dipole moment disturb its orientation, and at thermal equilibrium it make an angle, suppose theta. Theta is the angle of the dipole moment make with the external magnetic field. So potential energy of its dipole is equal to magnetic dipole moment into magnetic field intensity with a negative sign. So according to Boltzmann distribution law, Maxwell-Boltzmann distribution law, the magnetic dipole moment aligned at a particular direction is directly proportional to Boltzmann factor, that is directly proportional to Boltzmann factor e to the power minus E by kT. So we consider the magnetic dipole moment lying at theta and theta plus d theta is dn. Suppose dn is the number of dipole moment lying along the direction of magnetic field at an angle theta and theta plus d theta. So dn, theta and theta plus d theta number of theta, the magnetic dipole moment lying theta and theta plus d theta, that is within the solid angle, is proportional proportional to e to the power minus e by kt into d omega, where d omega is the solid angle. d omega is equal to 2 pi sin theta d theta. So the number of dipole moment lying theta and theta plus d theta is equal to dn, that is exponential minus e means mu into h by kt into 2 pi sin theta d theta, into 2 pi. So is dipole moment contribute along the direction of magnetic field is equal to mu cos theta. So the magnetic moment is magnetic dipole moment contribute the magnetic field along the direction of magnetic field is equal to mu cos theta. So total magnetic moment due to dn number of dipole, suppose dm, that is equal to mu cos theta into dn, that is equal to 2 pi mu exponential mu h by kt sin theta into cos theta d theta. So total magnetization due to all dipole, lying theta is equal to 0 to pi, that is equal to integration of dm 0 to pi integration of 2 pi mu exponential mu h by kt sin theta cos theta into d theta. Limit of the integration is 0 to pi. So average contribution of its dipole can be expressed as mu average. This is equal to total number of magnetization, total magnetization by total number of dipole, total magnetization is equal to m, that is m by n. N is the total number of dipole. N is equal to integration of dn. So average contribution total magnetization is equal to m and total number of dipole is equal to capital N. So average contribution mu average is equal to capital M by capital N, that is equal to integration of 0 to pi 2 pi mu exponential mu h by kt sin theta cos theta d theta divided by integration of 0 to pi exponential mu h by kt sin theta d theta. Now we take mu h by kt is equal to x. Suppose mu h by kt into cos theta Suppose mu h by kt is equal to x. X is equal to mu h by kt and cos theta is equal to y. Y is equal to cos theta. This is equal to x and cos theta is equal to y. Now replacing the value of mu h by kt and cos theta, we get mu average is equal to integration of integration of 2 pi mu exponential xy e to the power xy into y into dy divided by integration of 2 pi e to the power xy dy. The limit of the integration will be when theta is equal to 0, y is equal to plus 1. That means plus 1 to minus 1. So mu average by mu is equal to 2 pi cancel, integration of y e to the power xy dy by integration e to the power of xy dy. Limit of the integration is plus 1 to minus 1, The integration of e to the power xy dy, that is equal to e to the power xy by x, and y e to the power xy dy, that is equal to e to the power xy by x square into xy minus 1. The limit is equal to plus 1 to minus 1. Limit is equal to plus 1 to minus 1. So this is equal to, after simplification, e to the power xy, y e to the power xy by y, x minus e to the power xy by x square, limit is equal to plus 1 to minus 1, and e to the power xy by x plus 1 to minus 1. So putting the value of y, we get mu average by mu, that is equal to e to the power x plus e to the power minus x by e to the power x minus e to the power minus x minus 1 by x. E to the power x plus e to the power minus x, that is equal to 2 hyperbolic cos theta, 2 cos hyperbolic x, and e to the power x minus e to the power minus x, that is equal to 2 sin hyperbolic x minus 1 by x. 2 to cancel, cos hyperbolic x by sin hyperbolic x minus 1 by x, that is equal to cot hyperbolic x minus 1 by x, that is equal to mu average by mu. Suppose this is equal to Lx, where Lx is called Langevin function. The variation of Langevin function is plotted along x axis. Lx is plotted along x axis and x is plotted along x axis and Lx is plotted along y axis. The nature of curve is like that. Nature of curve gradually increase, and after high value of x it tend to saturated value. When x nearly equal to 0, at low value of x, the slope of the curve is equal to 1/3. That means Lx by x is equal to 1/3. Lx by x is equal to 1/3, or Lx is equal to x by 3. The Lx is equal to mu average by mu, average by mu. So mu average by mu is equal to x by 3. X is equal to mu h by x is equal to mu h by kt, mu h by 3 kt. So mu average is equal to mu square h by 3 kt. Average contribution of magnetic dipole moment is equal to mu square h by 3 kt. If n is the total number of dipole per unit volume, so total magnetization m can be expressed as m is equal to n into mu average, that is equal to n mu square h by 3 kt. Or magnetization per unit magnetic field intensity is equal to n mu square by 3 kt. 3 kt. The magnetization per unit intensity is called susceptibility. So susceptibility of a paramagnetic substance is equal to n mu square by 3 kt, or susceptibility chi is equal to C by T, where C is equal to n mu square by 3 k. This is called Curie constant. So susceptibility of a paramagnetic substance is inversely proportional to absolute temperature. If we plot the susceptibility chi along y axis and temperature along x axis, the nature of curve is like that. The nature of curve is like that. Next we discuss the quantum theory of paramagnetism. Quantum theory of paramagnetism. Also called Brillouin theory. Paramagnetism, quantum theory of paramagnetism, sometimes called Brillouin theory. In classical theory, we assume that the magnetic dipole moment are freely rotate. That means there are no interaction between two atom or molecule or dipole, and freely rotate is other. But and oriented and dipole moment are oriented along the magnetic field, oriented in any direction about external magnetic field. But quantum theory contradicts this statement, and quantum theory of paramagnetism, sometimes called Brillouin theory. In classical theory, we assume that the magnetic dipole moment are freely rotate about the magnetic field. But quantum theory contradicts this statement, and quantum theory tells that the magnetic dipole moment cannot align at any direction with the magnetic field, and the magnetic dipole moment and total angular moment is directly related by the equation mu is equal to minus g mu b into J. The magnetic dipole moment is directly related to the total angular momentum by the relation mu is equal to minus g mu b J, where J is the total angular momentum and J is equal to L plus S, where L is the orbital angular momentum, S is the spin angular momentum, and mu b is equal to E h cut by 2m is called Bohr magneton, and G is called spectroscopic splitting factor or sometimes called Landesi factor. The value of G is equal to 1 when the total angular momentum is arise due to the orbital motion, and equal to 2 when the total angular momentum arise due to the spin motion, and value of G is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2J into J plus 1. And the component of magnetic dipole moment along the direction of magnetic field, that is equal to mu z is equal to minus mj g mu b, where mj is called magnetic quantum number. The value of mj is equal to minus j2 plus j. So, is value of j, the magnetic quantum number mj take 2j plus 1, that means the magnetic dipole moment can oriented with 2j plus on different oriented. Magnetic dipole moment can oriented in 2 plus on different direction with the direction of magnetic field. So, potential energy of its dipole is equal to minus mu z into H. Mu z is equal to minus mj g mu b, mj g mu b into H. So, according to statistical mechanics or Maxwell-Boltzmann distribution law, the magnetic dipole moment oriented in a particular direction is directly proportional to Boltzmann factor, that is exponential minus E by kT, or that is equal to exponential mj g mu b H by kT. So, average contribution of magnetic dipole moment can be expressed as mu average, mu z average is equal to summation of mu z exponential mj g mu b H by kT by exponential mj g mu b H by kT, where mj summation of mj is minus j to plus j. Mj take the value, mj is equal to minus j to plus j, mj is equal to minus j to plus j. So, mu z is equal to g mu b mj exponential mj g mu b H by kT by exponential mj g mu b H by kT. A summation is taken over minus j to plus j, minus j to plus j. Now, we take two different cases when T is equal to high and H is equal to low. That means at high temperature and low magnetic field, this quantity is a fractional quantity. Suppose mj g mu b H by kT is equal to x. So, at low value of x means at high temperature and low magnetic field, the exponential factor can be expanded as exponential factor can be expressed as mu z is equal to g mu b summation of minus j to plus j mj on minus this quantity mj g mu b h by kt divided by summation of minus j2 plus j on minus mj g mu b h by kt. Now minus summation of minus j2 plus j into 1, that is equal to 2j plus 1 that I told earlier, and summation of minus j2 plus j mj, that is equal to 0, and summation of minus j2 plus j mj whole square, that is equal to summation of 0 to plus j 2 into 0 to plus j mj whole square is equal to j into j plus 1 into 2j plus 1 by 3. So mu z average is equal to this first term is 0 and second term minus mj whole square, that is g mu b into g mu b, g square mu b square, and mj square means j into j plus 1 2j plus 1 by 3 into kt 3 kt divided by this term is equal to 2j plus 1 and the second term summation of mj is equal to 0. So second term is cancel out or vanishes. So 2j plus 1 into 2j plus 1 is cancel. Or mu z average is equal to g square mu b square j into j plus 1 by 3 kt into h or mu z average is equal to g square j into j plus 1 suppose g square j into j plus 1 is equal to p effective whole square, where p effective means the effective number of Bohr magneton. So mu average is equal to g square mu b square p effective whole square h by 3 kt. So total magnetic moment or average magnetic moment is equal to mu square p effective square h by 3 kt. So total magnetization of a paramagnetic substance m is equal to average magnetic dipole moment into total number of dipole. Total number of dipole is equal to n into mu average, that is n into mu average mu b square p effective square H by 3 kT. So magnetization per unit magnetic field intensity H is equal to n mu b square p effective whole square by 3 kT. M by H, that is susceptibility chi of a paramagnetic substance, is equal to C by T, where C is equal to n mu is b square p effective square by 3k is called Curie constant. So the paramagnetic susceptibility of a paramagnetic substance is inversely proportional to the absolute temperature. So we plot the susceptibility of a substance along y axis and the absolute temperature along x axis. The nature of curve is rectangular, like this, rectangular hyperbola, and like that. So with increasing temperature, the susceptibility of a paramagnetic substance is decreases. This is known as Curie's law that I discussed in classical Langevin theory. At high magnetic field, it is found that when the magnetic field H is too high, then all the magnetic dipole moment align along the direction of magnetic field, and we get saturated magnetic dipole moment or saturated magnetic field magnetization. Magnetic field is high, then all the magnetic dipole moment align along the direction of magnetic field, and we get the total magnetization, and this magnetization is called saturation magnetization. It is denoted by MS.